Hello everyone. Can everyone hear me? Cool. Thanks for coming this evening for our lecture titled Tricks of the Light, How Nanoscale Materials Shape the World We See. My name is Andy Greenspon. I'm a fourth-year PhD student in Evelyn Hu's lab in the School of Engineering and Applied Sciences at Harvard. So here's a brief outline of what all three of us are going to talk about this evening. First, I'm going to talk about some basics of light waves and how they lead to some interesting natural phenomena that you've probably seen before. Then Christine is going to talk about how humans actually make very tiny structures called nanostructures, and how we can use these nanostructures to change the behavior of light to suit our needs. And lastly, Rob's going to talk about some modern nanostructures and how they manipulate light and how they lead to some modern applications. So let's just start at the very beginning. What is a wave? A wave is essentially some sort of repeating oscillation that travels through space. One that you're probably familiar with is a water wave in the ocean moving up and down. And a light wave actually behaves very similar to a water wave. Both of them have a crest, which is the high point of the wave, and a trough, which is the low point. Both of them have an amplitude, which for a water wave is just the height of the wave, and for a light wave is basically how bright the light will be. Both have a wavelength, which is just the distance between two crests, or two troughs. And both have a frequency, which is essentially how quickly the wave oscillates up and down, how many times it does that in a given amount of time. The main difference between a water wave and a light wave is water waves need water to move to be able to actually see them, whereas light waves are actually something called an electromagnetic wave, which is just oscillations of electric and magnetic fields moving through space, and they don't need a medium. They can just move in a vacuum. The other main difference is that light waves move incredibly fast. If you multiply the wavelength times the frequency, you'll get c, which is the speed of light, which in vacuum is a constant no matter how big the wave is. And that is 300 million meters per second. To put that in perspective, the time it would take if I turned on a light here for the light to reach Los Angeles would just be 14 milliseconds. And the light that's coming from the sun actually takes 8.3 minutes to get to Earth because of how vast the distance is. So as I said, light waves are electromagnetic waves, and we have this thing called the electromagnetic spectrum. And it essentially is just the range of sizes of these light waves and how scientists classify them according to these different names. So light waves, their wavelength can be anywhere from billions of meters long all the way to a fraction, small fraction of that. And just for reference, the average size of a human, say my height, is about here, 1.5 to 2 meters. Similarly, the frequency of the wave can go from 1 oscillation per second all the way to billions and billions and billions of times oscillating per second. The thing to note is that the wavelength times the frequency, as I said before, is actually a constant no matter the size of the wavelength. The frequency will always be different, such that if you multiply those two numbers together, you get the same speed when in a vacuum. And you're probably most familiar with this tiny section here, which is visible light. From the lights coming from here, you get white light, which is actually composed of all the colors of the rainbow. So anything that you see in this room is just due to visible light bouncing off it, and then that light hitting your eye. But you're also probably familiar with other types of light, even though you can't actually see them with your eye. Microwave ovens actually use microwaves to heat up food that you put inside, and microwaves are longer wavelength than visible light. You might also be familiar with radio towers that generate radio waves to transmit sound signals that you might pick up in your car radio receiver. And you might be familiar with X-rays, which can penetrate skin and scatter off bones so you can see if you have a broken bone or not. And as I said before, humans can only see this tiny, tiny fraction. And a lot of the light we see here is just white light from light bulbs, for example, but it's actually composed of a bunch of different wavelengths of light, the colors of the rainbow that you might be familiar with. And the range of the colors of the rainbow is actually only from 400 nanometers to 700 nanometers. Christine is later going to talk about the scale of things, but just for reference, 1 nanometer is 1/1000th of a meter, so extremely, extremely tiny waves. And you can also generate single wavelengths of light with lasers. For example, this laser pointer is only shooting green light. So I said that light moves at a constant speed in vacuum when there's no matter. But when light actually interacts with some sort of material, it slows down, in fact. And that can lead to some bizarre things like this pencil being sort of cut in this water. When it hits the water, you sort of see it's bent. And the question is, why is this happening? So it turns out that different materials actually cause light to move at different speeds. And this property of a material is just called the index of refraction. So if light will move slower when it's moving through water than in air, for example. Now, this difference in speed for different materials actually causes light to bend when it moves from one material to another. And sort of the simplest thing as an example is if I have a piece of glass and I have some sort of light to shoot through it, if that light is moving in one direction and then hits the interface between the glass and the air, it'll actually bend because of the difference in the index of refraction. And then it will bend again when it reaches the glass-air interface at the other side. So it'll end up coming out at a different angle. And I can just demonstrate this quickly right now with the help of Rob, holding up this piece of glass. So if I just shoot the laser pointer, it'll go in a straight line. But, yeah, if I go through the glass, you can see it's deflected way down there or up there. A little hard to align it straight. But you can see that if it goes through the glass, it'll end up going at a different angle from if I just shoot it through air. So the question is, I've demonstrated how this actually works, but in real life, but let's try to get a better idea of what's actually happening. And I think the best way to do that is with an analogy to a marching band. So in a marching band, you've got this guy, he's got beautiful colors and a poofy hat. And let's say we have a bunch of marchers in a line, and this is pavement they're walking on, and they don't realize it, but they're about to run into a bunch of sand, which is going to slow them down a lot. But because they're marchers, they'll all move at the same speed on pavement, but they'll also all move at the same speed when they're on a different but same speed when they're on sand. Excuse me for 1 second. Aha, thank you. Cool. Hit play there. Let's go back. Technical difficulties. Try that. There we go. Sorry about that. So you've got all these marchers moving in a line, and they're going to stay in their line. And when they hit here, you're going to notice the first marcher that hits the sand starts to slow down, which causes a kink in their nice little row. And so the marchers that are all finally in sand are staying in a row. The marchers that are still on pavement are in a row. But here, because this marcher is moving a little slower than this one because he hit the sand, there's this kink. And effectively, this kink moves through the row until they've all gone through the sand. And so you'll see when they continue going, a little bit distorted, but you can see that they've all ended up in a row again. But they're all moving at a different angle than when they came in. And so light actually behaves in pretty much the same way. You have a bunch of light waves where the light parts are the crests and the dark parts are the troughs, and the light is moving in this direction. And let's say it hits a material where it moves slower. You see this kink here, which is the same as the kink that was here. And at the end, the light is actually moving at a different angle because of moving from one boundary to another. So now that I've given this sort of more intuitive way of how light bends when it hits a material, how does this explain that pencil bend that we saw earlier? And the answer to that is that your eye is extremely deceiving. So if we imagine in this diagram a pencil in water, let's say there's light coming off the bottom of the pencil. Because the light is moving between water and air, that light will then bend, and let's say that light then hits your eye. But your eye doesn't know that it's bending when it goes between the water and the air. Your eye just tries to figure out in a straight line where the light was coming from. So your eye ends up actually seeing the pencil in a different place because that's where your eye thinks the light was coming from. And so here, it's a similar thing when you look at it from the side. the light is from the pencil in the water is coming out and bending, and so you actually see the pencil coming from here when you know from air it's actually a little bit shifted. And you can try this if you look into a pool of water and see something on the floor and then stick your head in the water so that the light doesn't have a chance to bend when it goes through the air. You'll see that they shift position if you're looking at the right angle. So how can we use this idea that light bends when it goes between an interface to our advantage? If you just had a thin piece of glass, as I showed, and send light through it, it'll just bend at an angle and go off in a direction. But if you carefully shape the glass for different thicknesses, for example, like this here, you end up with a lens. And light hitting different points here actually bends at different angles. And you can focus the light to a point. And that's effectively how your glasses work. And your eye itself has a lens, which causes light to be focused at the back of your eye. And then that information is transmitted to your brain. But if you have blurry vision, it means that your lens is not doing its job, and it's actually focusing the light somewhere else. So you put on glasses which basically behave as a corrective lens and refocus the light so that you actually get a crisp image. The other thing you're probably familiar with is a magnifying glass. And lenses can be shaped so that they magnify text, for example, from this tiny to this larger text. And this actually behaves in a similar way to the water glass bending the pencil. Because of how the light coming from the text is bent by this piece of glass here, it actually appears that the text is bigger to your eye, even though it's still the same size. So to summarize everything I've talked about so far, all light is part of this electromagnetic spectrum, whether X-rays, radio antennas, microwaves, and visible light. There are many interesting phenomena that can be explained with some simple optics, like a pencil being bent in water, or deflection of a laser when it hits a piece of glass. And we can use these simple principles of optics to design really important things, like eyeglasses and magnifying glasses. And with that, I'll pause and take the first set of questions. Yeah.
So with a prism, white light in, and you get other colored pop. So how come when you do the pencil or whatever, you wouldn't, if it was a multicolored pencil, how come that would be the...
So the question was, when you send a white light in a prism, you get a lot of colors out, which I will actually talk about in a second. But the other question was, if you have a pencil in water, how does if you had a multicolored pencil in water, why don't you end up?
Wouldn't it bend differently, so it'd be sort of warped?
Oh, you mean the different colors?
Yeah.
Oh, so the question is, if you had a pencil with a bunch of different colors, why doesn't a pencil end up getting warped? And I'll talk about how different colors bend in different ways, but just the short of it, I would say the colors aren't bent that much differently. Like blue and red aren't bent that much differently when they go between interfaces. So you don't actually see that much, you wouldn't see that much distortion if you had a multicolored pencil.
Do night vision goggles go outside the visual light spectrum?
The question is, do night vision goggles go out of the visible light spectrum? And I don't actually know how, and like real night vision goggles that, say, the Army uses or other people use, how they actually work, but I'm going to make since they can't use visible light because it's dark, I'm going to assume that they might pick up infrared heat from the body. Your bodies are emitting a lot of heat that we can't actually see, but it's actually infrared, which is a different type of light wave. And we can develop sensors that pick up different light, and it can convert it so that you see it as visible light. Cool. OK, I will continue on to the next segment then. So as I said before, if you have a single wavelength of light, and I showed if you send that light through a piece of glass at an angle, you end up with the light being deflected to a different angle. But as the member of the audience said, if you have white light enter a prism, a piece of glass, you end up with this deflection also, but what comes out deflected is actually a rainbow. And this is an actual prism demonstrating that effect. So the question is, why for the single wavelength of light do you just get a single wavelength out, but with white light you get a rainbow? And as I said earlier, white light is actually all the colors of the rainbow just put together, and our eye sees it as white light. And the answer is that index of refraction is actually a little tricky, and depending on the index of refraction of a material depends on the wavelength. So very, very slightly. So that different wavelengths actually end up bending at different angles when they hit this boundary. And so you don't see it in everyday life that often, but if you have white light hitting something, say a piece of glass, this prism, the blue and the red and the purple, they all bend at very slightly different angles so that when they're traveling through the glass, they start to separate. And so when they come out at the other end, your eye can distinguish spatially that one is at one position and one is at another. And you can do this too with, let's say this is a rain droplet. You have white light coming in, and the red and the purple bend at slightly different angles, so they start to separate. They reflect off, let's say, the back of this rain droplet and continue separating until they bend again when they hit air, and you have a rainbow come out. And you might wonder, why do we care about rain droplets separating light? And you've probably seen this before as a rainbow. This is basically how a rainbow works. A bunch of water droplets floating in the air, and you see the sort of summation of all of this deflection. And the only other thing I'm going to note here is that here you might be able to see a very faint double rainbow, ever elusive. And and the reason that you get a double rainbow is if the light actually bounces a second time in this rain droplet and goes off at a different angle. So the light from this first reflection gives you the first rainbow, and much less light is reflected a second time and goes off at a different direction. So that's why the double rainbow, the second rainbow, is very faint and you don't always see it. So I've talked about how light interacts in matter, how matter bends light and separates out white light into its constituent colors. But as I said, light is a wave, and waves can actually influence each other. They interfere with each other. And this is known as constructive and destructive interference. So if you have two waves next to each other moving along, and let's say the troughs align, and so the crests will align, let's say they're the same wavelength of light. If these end up aligning, they'll actually sum together, and you end up with a wave, in this case, with twice the amplitude because these amplitudes are equal. Similarly, if you have two waves that are next to each other and the trough and the crest align here, and then the crest and the trough align here, and if they happen to be the same amplitude, they'll effectively cancel each other out, kind of like a subtraction. And so you'll actually see no light here. And this is somewhat abstract, but you actually can see this just walking down the street, and you probably have and not really thought about it, from an oil slick. That might be coming from a car or a truck, and you might see all these colors. And these colors actually come from a different phenomenon than the rainbow from the rain droplets. You notice this isn't really a rainbow, but a bunch of different colors. And the reason this occurs is you have light from the sun coming in, and light from the sun, some of it will bounce off the top of the oil, and some will bounce off the bottom of the oil. But that white light is actually a bunch of different wavelengths of the rainbow. So you can look at each wavelength individually. So if we're at this point where there's light blue color coming from the oil, you could look at just the light blue. And it turns out that if you look at the light bouncing from the bottom, the light blue bouncing from the bottom of the oil, and the light blue bouncing from the top of the oil, it turns out that the crests from both of those light waves end up lining up. And so you get constructive interference. So you see this nice blue color. But if you took any other color wavelength, let's say this pink here, the pink wave bouncing from the bottom of the oil and the top of the oil, the crest and the trough of those align. So you get destructive interference. So they just cancel, and you don't actually see any light. And if we move to a different position, you see this different color, pink, and it's actually because the oil is a different thickness here. And because it's a different thickness and all these colors have different wavelengths, you end up with a situation such that the light blue that constructively interfered before, now the crests and the troughs align for the light blue, and so you get destructive interference. But the pink, bouncing from the bottom of the oil and the top of the oil, those two light waves, the crests align, and you end up with this nice pink color. So all these different colors are actually slight variations in the thickness of the oil. So the last thing I'm going to talk about is how nature actually manipulates light to its own advantage, and that's in butterfly wings. So here's the top of two butterflies. Their wings, one is yellow and one is blue. This yellow is called pigment color, and it actually comes from a dye inside the wings. that absorbs all light except for yellow and reflects yellow light. So you end up seeing a yellow color. But this blue isn't actually because of some sort of blue dye that absorbs all light except blue and reflects blue light. If you zoom in a lot, and Christine will talk about how we do this, and this is called structural color, you can see these sort of Christmas tree-like rods that make up this wing. And they look extremely complex compared to the oil slick, but the principle is actually the same. Blue light coming in here and bouncing in a position here and say here next to it will bounce off, and it ends up that blue light will interfere constructively. So you see this nice iridescent blue, but all other colors that bounce off here will interfere destructively, so you don't see any other color. And you can make this even more apparent if you flip over the wings and look at the bottom, and you can look at these afterward. The yellow is still yellow, more or less. It's still the same dye, but the back of this blue one is actually brown. And this brown is actually due to just brown pigment, brown dye molecules. And you can see that this is the top and has this repeating pattern, but the bottom here doesn't have any sort of pattern. It doesn't cause this sort of interference. So if you're looking at the wing from the bottom, you just see this dye. But if you flip it over and look from the top, you get this interesting structural interference effect. So to summarize what we've talked about in this section, the complex behavior of materials allows you to separate white light out into the constituent colors of the rainbow, so you get prisms and water droplets to give you beautiful rainbow colors. Light, because it's a wave, can actually interfere with itself, and you can see this from thin films like oil slicks on the ground. And nature has actually developed complex nanostructures to manipulate light to give you these iridescent blue colors. And in the next section, Christine's going to talk about how we want to try to mimic these things in nature to have light do what we want it to do for our purposes. Questions? Oh, yes.
What's the difference between like paint or like dye, like you said, and light, like through a filter, putting a filter in from the screen and how they mix and interact? Is there a difference? You
mean like a filter that would let only one light color through? The question is, what's the difference between sort of a paint of one color and maybe a filter or a screen that would let some sort of light through? I think it would depend on the type, but I'm pretty sure for paint, there's different chemicals in it that absorb some light and reflect other light, so it behaves like a dye. It might be made of more complex chemicals. And filters that only allow a specific color light through, it actually can depend. The filters that we use in, say, my lab, they are structural, so they have different thicknesses of glass, so that different light bounces off of them and interferes destructively, and you only get a certain light color through. So they are different.
If I go to the butterfly exhibit at the Museum of Science, and I look at 100 different species of butterflies, and they're all different colors, will there be one or two that use this structural color, or is it more like what's the, how common is that for the butterflies?
The question is, if you go to the Museum of Science, for example, or Museum of Natural History, you'll see all different types of butterflies with different colors, and how common is structural versus pigment color. And I honestly don't know the answer to that, but that's definitely an interesting question, because I'm not sure how often this is harnessed in nature. Cool. And with that, I'll pass it off to Christine. I turned that one off for a second.
This one is off now? That's
Sorry about that.
the back. Yeah. Let's put this one to this side. All right, this turned on?
Yeah.
Cool.
Turn this one on.
All right, all mic'd up here. maybe. There we go. Okay, so can everyone hear me well now? Great. Okay, so what Andy just talked about, he gave us a really good introduction to light and how its properties work. And what I'm going to talk about now is how we can mimic these things that we see in nature in the lab and actually make structures that are quite similar ourselves. Before we do that, there's something really important that I want to discuss. Andy mentioned that visible wavelengths of light are about 400 to 700 nanometers. This is a term you may have heard before, but what does that actually mean? Units you're probably more familiar with are something like a meter and a millimeter. So a meter, about yay big. A millimeter is about the thickness of, say, the thin part of a dime. That's about a millimeter or so. And then there's micrometers, which is the next line here. And those are about 1,000 times smaller than a millimeter. And 1,000 times smaller than that, or as Andy mentioned earlier, about 1 billion per meter is a nanometer. There's one thing that I want to point out here that's important. So I called this a micrometer, and you actually may have heard I first said micron. This is a term that I just want to make sure you guys are familiar with because it's something that is just used colloquially. It's just a shortened version of micrometer. So if you hear us saying that, it just means that there are 10 to the 6th micrometers or microns in a meter, or that there are 1,000 nanometers in a micron. So still, this is probably just confusing. Lots of zeros and numbers. You're like, I still don't know how small it is. This is not helping. And so what I want to do is give you guys a little bit of an analogy here. So we know that the distance between Boston and San Francisco, if we just draw a straight line, is over 4,000 kilometers. It's far. But what we're going to do is just take a minute here and imagine that it's actually a millimeter. So it's actually the thickness of a dime in what we're assuming right now between those, the thin direction of the dime. And if we use that analogy, then the distance now between the auditorium that we're in at this moment and Harvard Square is actually similar to the distance of what a micron would be, so about 1,000 times shorter. And remember, this is the larger of our two small units. So if we go even 1,000 times smaller than that, we get to what a nanometer is. And so that distance, if we sit here and think, well, what's a nanometer on this scale? It's actually about the distance across our screen here, about 4 meters. So nanometers are very, very small. The stuff that we're making is tiny. Okay, so how do we see anything if we make it that small? Andy mentioned that when we see things, it's using our eyes, and we're using visible light, which is 400 to 700 nanometers. If we want to look at stuff this small, we use often a light microscope, but this has a limit, which is around a few hundred nanometers. And sometimes we want to see things even smaller than that. So how do we do that? Well, if you imagine that you have a pond, imagine you have a pond of water and you have this large rock in the water. And you send some waves at that rock, and when they get there, they'll start bouncing off. They'll be deflected in all different directions. And so this basically allows you to see that rock. You know that the rock is there. But if you put a small pebble in the water and you send that same wave that has the same wavelengths like we talked about earlier, it won't even get distorted at all. The wave will just pass right over that pebble as if it wasn't even there. So what we do to see things that are smaller is we want to use a smaller wavelength that can see that it's there. And how we do this in the lab is using something called an electron microscope, which allows us to see things down to about 1 nanometer in scale, so very small. This is a picture of just what an electron microscope looks like. You put your sample in here and you actually control it through a computer. And to give you guys a sense of what this looks like when you're using one, I have a little video I want to show you. So we're going to start with this image. This image is what you would see if you looked into a normal light microscope. The distance across the whole thing here is about 6 millimeters, so that's about as wide as your pinky nail. And as we start zooming in here, you'll start to see that these spherical objects start to come into focus. These spherical objects are tiny glass beads, and they have a diameter across them that's about 10 microns. That's on a similar size scale to a red blood cell. So they're pretty small, and this is by no means at the limit of what this tool can do, but as you can see, we're now at 12,000 times magnification of the actual size of this object, and we can go even bigger. We can just keep going if we want to. So that's really helpful when we're making these small structures. So going back to what Andy started talking about earlier, there's all of these things in nature that we see that have all these colorful effects. He already showed us one example of a particular butterfly wing. If we look at this particular shell here, you can see that it has this iridescent quality to it. When we put this under the microscope, so we take a slice out right here, and we put that slice under the microscope and we look at it, what we actually see is a structure that looks like this. So it's a bunch of layers of thin films on top of each other. So what's happening? Well, Andy mentioned earlier that we have this thing called thin film interference, where if you put in light, you can have a thin film that can constructively interfere and allow you to reflect certain colors of light. What we have here is a whole bunch of different layers that are all different thicknesses, and when we put in light, they all reflect different colors. So we just end up with this white, shiny looking material. Another example that we can look at, so you asked earlier about how many butterflies use this. There's actually also peacocks are known to use this structural color. So you can see a peacock wing here, peacock feather, sorry, excuse me. And you can see that this also exhibits structural color. It's a slightly different pattern than we saw earlier, but this by nature over many years has been basically perfected so that it reflects these blues and greens that you see here. There's an important thing I want to point out on this slide, and that's the scale bars. So if you look at these white bars in these two pictures, each of those bars represents a distance of 1.5 microns or 1,500 nanometers. And we talked about visible light being about 400 to 700 nanometers. So as a general rule, when you're looking for these kinds of colorful effects in nature, the size of the structures that you'll see, so these lines or these thickness of these layers, the size of all these different features may have different designs, which have their own complexities, but they'll all be on about the same size scale, which is very similar to the wavelength of light. Okay, so far what I've talked about is the size scale of things, how small a nanometer is. I've told you really just how small that is, but that we can see it by using this tool called an electron microscope. And then I've mentioned just briefly that by looking at natural structures using this electron microscope, we're able to see that if we want to create these colorful effects, we want features that have about the same size scale as the order of wavelength that we're looking at. So with that, before I move on, do I have any questions from you guys yet? Okay, keep going. All right, so I've told you about these small things, but is it possible for us to even make them? It turns out the answer, as you may have guessed, is yes, we can actually make them. We can't just look at them in nature. We've been doing this for a very long time in electronics. And there's this popular law known as Moore's law, which actually explains this. And it's actually not a physical law. I just want to delineate that. It's actually an observation. But what this law says is there was, in the mid-19th century, there was basically a revolution of electronics when the transistor was invented. And what the transistor is basically the building block of all of our modern day computer chips, everything that we use. And you can think of it as a switch that basically just can turn on and off and send information throughout your computer. And what Moore said, he was one of the co-founders of Intel actually, and what he said was that he noticed that every 1 or 2 years, the number of these small transistors on a computer chip was doubling. But if we want to keep these computer chips about the same size and we keep doubling the number of transistors, we need to make them smaller, otherwise our computers are going to keep getting bigger and bigger, and clearly we don't want that to happen. And so what he predicted was that this trend of them shrinking in size would continue, that every 1 or 2 years they would shrink further and further and further. And so basically what we can see here, if we look at this graph, is that by this point now in 2014, we have these electronic chips that are these transistors that are all the way down to 14 nanometers. So if you remember from earlier how small a nanometer was, we're able to make things that are very small. And again, why am I telling you about this? The reason I'm telling you about this is because we can use these same techniques to make optical nanostructures that they do in electronic devices that we all have in our cell phones and computers. So what is that process called? That process is called nanofabrication. Sounds just like what it means, fabricating very small things. And how do we do that? So we start with something, I'll give you first an overview and then I'll go through it in more detail. So we start with something called a substrate. So this is the material that's underneath everything we want to build. On top of that, we usually start with a thin film of some sort of material that we want to pattern. The first thing that we do is photolithography. So this is a process I will talk about, but what this helps us do is create a temporary pattern on top of our thin film. And that could be anything we want. It could be squares or lines, circles, anything you want it to be, you can make that pattern. Once we have that pattern, there's two main things we can do. We can either do a deposition to add some new material, or we can do something called etching to remove some of that material. So let's step through this in a little more detail so that you guys have a good sense of what I mean by this. So we start at the beginning, we have our substrate, and we have a thin film of some material on top that we want to pattern into something. We start with the first step, which is called photolithography, and we like to call this writing with light, as you'll see for a good reason. And the first step here is to add a material called a photoresist on top. And what this photoresist is it's a material that is sensitive to light. So just like when you take pictures in an old camera, there's film in there that will be exposed to light and it will change chemically. We do a similar thing here. So we put down photoresist, and then we have a mask, which is usually a big piece of glass with some metal printed on it. When you shine ultraviolet light through this mask, there's parts which are transparent. Oops, sorry. There's parts which are transparent, as you can see here, and then other parts which are opaque, so the light cannot go through them. As you shine that light through, the parts where the light shines through chemically change because of that light. And if you take that sample and you now put it into something called a developer, just like you develop film, the chemical can wash away that part that was changed in structure by the light. And so what you're left with is this temporary patterned mask on top of the surface. So as I mentioned at the beginning, there's two things you can do once you make this temporary mask on top. You can either add material or remove material. So the first thing we're gonna talk about is adding material. We call this deposition. Just as you expect, when we add material, it goes everywhere. It goes not just in the holes we left, but it also goes on top of the pattern that we made. So what you have to do is, again, put it in a chemical which can remove the photoresist, a different chemical than before, but a chemical which can remove the photoresist that was not exposed to light. So when you do that, you end up with the pattern that we wanted earlier. So I mentioned that once you make this temporary pattern using photolithography, you can do two things: deposit, like we just showed, or if you don't want to add a new material, you can take away material from the film that you started with. So let's talk about how we do that. So we have this photoresist mask, this temporary mask, and we're going to do something called etching. So the way that this works is you take particles, usually highly energized particles, and you can bombard them down at the surface. In the places where you have this red mask, it will protect the material that's underneath. But in the places that you don't, when you bombard it, it will get etched away and removed. So in that way, you can remove part of the film that was there before, again, with whatever pattern you want. Again, just like we did in deposition, you can put this in a chemical, remove your temporary mask, and then you have the structure that you wanted. So these are just a few examples of the different steps you can do. You can imagine we can layer them with many different materials and different orders and different patterns, and we can really just end up creating any kind of pattern we want that way. And so what I want to do is go through two examples of how we can use this type of patterning to mimic some of the natural patterns and create them in the lab that we saw earlier. So the first one is thin film interference. And this is what Andy was talking about with the oil slick, where you could see the different colors when there were different thicknesses of film. So this one is pretty easy for us to do in the lab, actually. We don't even need a pattern, so that's great. All we do is take our substrate and we deposit different thicknesses of thin film on different parts of the material. So when we do this, normally, we've done this on silicon, which I have an example you can look at over here later. It's a gray in color. And normally, the film that we're depositing onto this is actually transparent. But when we put these different thicknesses of films on here, you can see that the color is different depending on the thickness of the film. And that's because of this constructive and deconstructive interference that Andy just explained. Why is this useful? Well, it's actually used very heavily in things like anti-reflection coatings, like on your glasses. They actually use it on airplane windshields. They use it all over the place, so you don't get reflections when you don't want them. And in optical filters, someone asked a question earlier about optical filters. This is one way you can make them to reflect or transmit certain wavelengths of light. The second example I want to go through is something more like structural color, so something more like the peacock or the butterfly that we talked about. And here's an example of a structure that is simplified but looks very similar to these structures. And if you look at this from the side view, this actually looks exactly like what we saw when we were just talking about etching in the nanofabrication steps, where the dark gray part is the substrate and the light gray part on top was that thin film that we etched into. If you look at the top view, this is an electron microscope image, and you can see that these are not just little points, but they're actually ridges. They're long lines that run the whole structure of this film. And if we just look at this using our eyes, we can see that this film actually has a lot of grade. It looks like it's called a grating, and it has a lot of different colors. A unique property of a grating is that as you change the angle, you change the color of light that you see reflected from that. So I took something called a dark field microscope image, which we can talk about later, just to intensify this effect. And you can see that the colors really show here, that these are just the same sample, but just looking at it from different angles. This is something you've definitely seen before. If you have an ID, a passport, anything that's an important document, it might have a hologram on it. When you change the angle, you'll see the colors changing when you move that around. Also, a CD and DVD, those have ridges on them, which are very similar to the structure, and the color will change as you're moving around. So as you probably have guessed, nanofabrication is not that easy. There's a lot of steps. These things are very small. And we can't actually just do it in a normal lab. So this is a part I haven't talked about yet. We actually have to work in a clean room, what's called a clean room. And this is to avoid contamination of our small pieces. So a clean room, what it is, it's a room that just has a very small number of large particles in it that are contaminating it. So if you looked at a clean room at something that produces computer chips, like at Intel, that would be a very clean room, so to speak. And in a volume of air that is about 1 meter cubed, so imagine again 1 meter by 1 meter by 1 meter, they'll only have 0 to 3 particles which are bigger than 5 microns in diameter. So that's around, again, the size of a red blood cell. Very, very few particles in that air. If you compare this to the air, like in the room we're sitting in, just normal air, we have about 300,000 particles of the same size in normal air. Where does this contamination come from? It turns out that it's mostly from us. So when we work in the clean room, here's a picture of me in the clean room. We have to wear these things called bunny suits. And these bunny suits aren't to protect us from the things in the lab. Like I mentioned, they're to protect our samples and the things that we're making from us. Because as we're in the clean room, we're shedding hair, we're shedding skin, we have oils and sweat on us. There's textiles, there's stuff from our clothes that can get on them. All of these things are just huge compared to the scale of the things we're making, and they can just destroy it. So we wear these suits to help keep that from happening. And we actually have some of them if anyone wants to try them on later and take some photos. We have some. That's something that people tend to like to do when they come to visit us. I know I do it myself, actually. So feel free if at the end of the lecture later. So to summarize everything I've talked about so far, or to this point, before we take our break, we're able to make all of these nanoscale structures that we see in nature through this nanofabrication process, a combination of photolithography, etching, and deposition. And we do this all in a clean room because we want to make sure that we don't have contamination. In the next part of the final part of the talk, you'll hear from Rob, and he's going to talk about more of the applications we see in everyday life. And then what's really cool is he's going to actually talk about the structures that we can now make in the lab, which allow us to make properties which go beyond what we actually can see in nature, including things like invisibility, cloaks, which clearly don't just exist in nature. So before we get to that part in the break, are there any questions on this section? Yes?
Well, you mentioned using ultraviolet light for the photolithography, but if the semiconductor fabs are making 14 nanometer transistors, they can't be doing that with UV, right?
Yeah, so this is a great question. So the question was that I mentioned that photolithography is done using ultraviolet light. So ultraviolet light has wavelength which is around 300s of nanometers. And the question was, the semiconductor fabs are making transistors and other components which are down at 14 nanometers. So how can they be making something that's 14 nanometers with wavelength that has a light of 300 nanometers? The reason is because they're not. You're totally right. Well, actually, so there's a couple of things here. So I don't know the details of how exactly they do it, because there's some proprietary things there. But there's a way to make devices much smaller that we use in research labs, which is actually called electron beam lithography. So instead of using photolithography, where we use light, you can use electrons. Just like we were talking about with a light microscope versus an electron microscope being able to see smaller, we can use electrons to write a lot smaller. So that's one way that you can make smaller devices. I don't know their secrets about exactly how they do it, but that's one trick you can play.
When you create a sample, how do you debug it?
Yeah, so the question here is, when you create a sample, how can you debug it? And you can hear my colleagues over here just busting out laughing. It's hard. So the main ways to debug it are to try to record all of the steps that you're taking. So make sure you keep really good notes of exactly, you know, what temperature you do something at for how many seconds, what the power was, you know, maybe if it rained that day. You know, anything you can keep track of is very helpful. And then also, if you can stop in between certain steps when you're starting a new process and take some measurements there. So something I didn't really talk about is what you do to see if something is working. So you can stop after one of these steps. I went through many steps. Do some measurements and see if it looks like what you expect. If it doesn't, try to figure out why and then start over. So it's a very iterative process. Yeah, great questions. Anyone else? Okay, well, thank you guys so much.
Thank you. My name is Rob Devlin, and I'm an applied physics PhD student, and I work in the lab of Federico Capasso. And so Andy gave us a really good introduction to what is light and how it interacts with natural materials, and how these materials actually shape light on the nanoscale. Christine talked a little bit about how then we can make these nanostructures in the lab and start to use them for our own means. What I'm going to talk about is how we take both of those elements, the understanding of light and the understanding of making things very small, and we slam them together into actual applications. So before that, I want to take a step back. Why do we want to apply this? And one of the reasons Christine already mentioned a little bit, which is this idea of shrinking information down to smaller and smaller densities. We have computer chips now that essentially 94% of all man-made information is stored on computer chips. So we've been making these chips really small. We have about 2 billion transistors on a single computer chip now, which is approaching the number of stars in the galaxy. So we've been making these things small and storing our information. But there's a problem. When we want to access this information on our home computers, for example, or on the internet, since there's so much information we're trying to transfer, the normal electronic cables that we use are just too slow to transfer that information. So we're essentially, the demand from the users now is so high that we can't transfer information with electricity anymore. So now we've moved to essentially what is called the optical information age, where we're actually using light now to transfer our information because it's much faster than these electronics. So in analogy to an electronic cable, when we transfer information with light, we use something called an optical fiber. So now we're beaming light down this optical fiber. It actually looks a lot like an electronic cable. We have some sort of protective coating here. But in the middle, instead of having a wire, we essentially have a glass tube. and this glass tube acts to guide our light. So we put our information on a light beam, and we encode it just by simply turning the light on and the light off, almost like sending electrical pulses. We shoot it down this optical fiber, and these lay out across entire countries, so across the US or across oceans. And then at the speed of light, our information beams down this and ends up on the other side, transmitted to our computers. So as I said, we're doing this at the speed of light, and we have nothing that can travel faster than the speed of light. So this allows us to actually get to these unprecedented rates of information transfer. Specifically, there's this new record of 50 terabits per second, which is a 50 followed by 12 zeros of information being transferred. Now that's just a huge number, and I have no idea what it means. But to put a little more physical context to it, this would be like having 100,000 newspapers delivered to your doorstep every second. That's the rate that we can do, because we're going at the speed of light. So this is all great. We now have this way to transfer our information faster, but there's a problem. So we go at the speed of light and we transfer this across the country, across the ocean, and we get to the end of the line and we convert it back into electronics. So we've done this at the speed of light, but now we're going back into an electronic chip. So what we would really like to do is develop new technologies and new techniques to control light on the nanoscale so that we can take it, shoot it down our optical fiber, and then keep our information as light and keep transferring it around the computer chips as light. So it turns out that nature is already really good at this, as both Andy and Christine have pointed out. In butterfly wings, they're already manipulating light on the nanoscale. And so as we often do in science and engineering, when we're first starting out in something, we turn to nature for inspiration. So what we do is we make something called man-made butterfly wings, or photonic crystals. So photonic is just another word for light, essentially, and we call them crystals because they have this really regular repeating structure. So this is very similar to an atomic crystal, where, for example, if you have a diamond and then you have the element carbon, it repeats on a very regular distance, and so it has this nice ordered structure. In contrast with our photonic crystals that we're making that are like these butterfly wings, what we have again is we have a very nice repeating pattern, but instead of using atoms or elements that differ, light interacts with different indices of refraction. So what we do is we'll take, say, we'll etch, like Christine had mentioned, a hole into a background of glass, and we'll repeat this on a very regular pattern. And this will allow us eventually to have constructive and destructive interference, but for our own technology and to our own ends. Another thing to note is that the scale of the photonic crystal, Christine mentioned this as well, that our spacing between our air holes in this case is about the order of the wavelength of visible light, so around 500 nanometers. Whereas the spacing in an atom is about 1,000 times smaller. So we really tailor our materials to give us the properties that we want. Okay, so let's just have a look at what this would look like if we actually made one. This is an electron microscope image of a photonic crystal. And again, we can see we have some hole with one index of refraction, and then it's in a background of glass with a different index of refraction. And then we're separated by about the length of the wavelength. And to give a little more perspective, this entire structure here would fit quite nicely on a red blood cell. So Christine talked about just how small that is. So we can now make these structures in the lab, except we're going to apply them to the technologies that we want rather than just what nature gives us. So we talked a little bit about filters, and we talked about how in the butterfly wing a specific color gets enhanced, for example blue. All the other colors get canceled destructively, blue adds up constructively, we get this nice blue color. What we can do here is we can design a photonic crystal instead to cancel one specific color. So if I make these spacings just right to cancel out a specific color, I can shine blue on it, and that'll pass through my photonic crystal as if it's almost not there. I can similarly shine the color red on it, and it'll pass through almost as if it's not there. But again, if I make these spacings just right, when I shine green on this photonic crystal, it destructively interferes everywhere. So essentially what I've done is I've made a material where the color green simply cannot exist. Now, green might be kind of sad and lonely right now. It's not joining its friends passing through this photonic crystal. But we can actually use this to our advantage to start moving towards guiding light on the chip scale, on a similar scale as electronics. So if I come here and now I take my photonic crystal, you can see I have a photonic crystal up top here and I have a photonic crystal down on the bottom, but I've removed it in certain places. So I've made this essentially L-shaped through my photonic crystal. Now, we know from before that if I design this properly and I shine my green light on it, it's going to bounce off at the top and it'll bounce off at the bottom. But there's an interesting question is, what happens if I take my green light and I shine it here? So because there's no photonic crystal there, the light will actually be guided through. Almost as if we have a wire now that we would normally use to guide electricity. We have a wire on a chip scale that we can guide light. And it can even do sort of interesting things like turn 90-degree corners. And we can now take our fiber that has transferred our information at the speed of light across oceans, across countries, and then we can keep the information as light and continue to guide it around on our chips. So this is sort of a way that we've been mimicking nature to get to being able to guide light at similar scales as electronics. We're not quite as small yet, but we're getting down to the scale of electronic chips. So I'll just quickly summarize here. We're now in the optical information age, and much of the information we get on our computers and our smart devices is being transmitted on beams of light. We first have turned to nature for inspiration in how to design these structures that we want to ultimately use for our technologies. And now we're to the point where we're starting to make optical circuits on length scales that are approaching electronics and allowing us to keep our information as light. And I'll pause for questions. Yeah?
Is that how SSD drives work?
How, I'm sorry, one more time?
SSD drive, a solid state drive, as opposed to liquid?
So the question is that how a solid state drive works? My understanding is no, that a solid state drive is still all electronic. But there are some audio systems that will actually use optical fibers to transfer the information.
So what's the 0 and the 1?
So, good question. The question is, what is the 0 and 1 in light? And if I come back to my optical fiber picture here, essentially what we're doing is we're simply turning pulses of light on and off. So this is essentially a high intensity of light or a low intensity of light. And at the end, when I do convert this eventually back into electronic signal, you'll see an electronic pulse from this light pulse.
Are they sending regular light, or is it laser light through the fiber?
It's typically laser light. So to have everything travel and end up in the signal that you originally sent, you need what's called coherent light. We don't go into that here, but that's what you get out of a laser. It's different than the light that you would see coming out of a lamp, for example. And they actually do this not with visible light right now, but with light in the infrared, so 1550 nanometers. So 700 is the top of the visible. We're about twice that wavelength.
And when you're up at Terra, though, you're pushing past the nano frequency. How many different frequencies are going simultaneously through the fibers?
I don't have the exact number off the top of my head right now, but there are a number of different frequencies that you're pushing through, and it is extremely fast, as you noted. Did you also have a?
You just answered my first question.
Sure.
It's not white light then, it's another frequency.
Yeah, so this is laser light, and it's specifically laser light that is longer than visible wavelength.
Okay, is it really traveling at the speed of light, or is it almost the speed of light because of the medium?
That's a great question. So it's actually, as Andy pointed out, when light goes from, say, air or vacuum into a different medium, it will slow down slightly. So for example, in glass, you have an index of refraction which is about 1.5. And so you would divide the normal speed of light, which is 3 times 10 to the 8th, divided by 1.5, and that's how fast it's traveling. Okay, so flip back through here. Now, so far what we've talked about is taking cues from nature and designing materials on the length scale of the wavelength. So in our photonic crystal, our spacing was about the visible wavelength. But what we want to know is, can we go beyond the natural materials that we see? Can we give materials new functionality by designing them a specific way? And what happens, and can we design materials that are even smaller than the wavelengths of the light? The answer to this is of course yes, otherwise this would be a really anticlimactic part of the talk. And so what we do is we make something that we call metamaterials, where meta comes from Greek for above or beyond. So now what we're doing in the lab is we're making specific nanostructures that give us new properties that you don't see in natural materials. So really, generally, what we have, if we have a normal material and I have my light wave shining on it, out of the other end of the material, the light wave comes out largely undistorted. If you shine it at an angle, it may bend, as Andy showed. It may scatter a little bit, but my wave looks mostly the same. But what I want to be able to do with the material is I want to be able to design it so that the wave comes out however I want it shaped, going in whatever direction I want. So what we do is now we put a metamaterial in the way of our wave, and I can basically make my wave look however I want coming out of the other end. And then if I look at each one of these little circles here, this would represent maybe 1 unit of my metamaterial. And whereas my photonic crystal was about 500 nanometers between each unit, in my metamaterial, I have about 10 to 50 nanometers between each unit. So I'm about 10 times smaller than the wavelength that I'm using. And this gives me incredible spatial resolution to send light wherever I want to send it. So this is a really important design tool that we're now using that allows us to send an arbitrary amount of light, so the amplitude or the intensity that Andy talked about, in whatever direction I want. So what exactly do we use to do this? We use techniques that Christine talked about. So I can put materials down on a substrate, for example, and now instead of having a nice regular pattern like a photonic crystal and having a spacing on the order of the wavelength, I can make them whatever shape I want. I can change the distance between their neighbors, and this gives me sort of unprecedented control over the wave that I get out at the end of my metamaterial. We can similarly do this with something that a lot of people are familiar with, which are antennas, but we're making antennas on the nanoscale. So again, we're much, much smaller than the wavelength of light, and each one of these antennas, depending on its shape, its orientation, how close it is to its neighbor, allows me to take my incoming wave and send it in whatever direction I want. So these are some of the nanostructures that we actually make in our lab. So again, you can see on the top we have a bunch of pillars, much smaller than the wavelength, where I have these nano antennas. But the theme of this talk has been the scale of things. So coming back once again to just how small are we making these metamaterials. So we saw that if I have my photonic crystal, it would fit quite nicely on the red blood cell. And I think we've mentioned red blood cell about 15 times in this talk, so if nothing else, you'll know what the size of a red blood cell is. And so now if I take my metamaterial, this actually fits in 1 unit of the actual photonic crystal. So this is giving me unprecedented control over my light beam that is hitting my material and allowing me to design new technologies. So now if I go back to this picture, I can put my nano antennas in the way of this beam and I can send it in whatever direction I please. So what does that mean? What does that let us do? Andy talked about how if I have this glass of water and I see the straw bend, it's because there's a refractive index difference between the air and the water, and it causes it to bend. So this is sort of a normal picture. We've seen this in pools. We've seen this in water. Hopefully, though, this makes you less comfortable. Where now with the metamaterials, because I can send my light in whatever direction I want, I can actually turn light on its head. And we can now have something that we call negative refraction, where light essentially bends the wrong way. And this is by changing those little units to each send light in a specific direction. In terms of technologies, so this has all sort of been really interesting and cool pure science, but in terms of technology, because we can bend light in the wrong way, we can start to move to more, say, science fiction or fantasy type applications. For example, we can move to making invisibility cloaks, popularized by a certain wizard. So essentially what you want with a visibility cloak is you want some sort of material that you can put on, and the light that's behind me, or whatever's coming from behind me, would pass through to your eye as if I wasn't there. So this is not a real invisibility cloak. This is an artist's dramatization, so we don't have this yet. But what we can start to do is take really small particles, for example. So if I look on the left, this would be without my invisibility cloak. And as Christine pointed out, if I have a particle and each one of these lines represents my wave, the particle is going to scatter this, it's going to distort the wave, and then that distortion is going to be what I see, and I perceive there being something there. But now if I say, where this circle is, I put a cloak with my metamaterial that can send light in whatever direction I design it for. I can perfectly cancel out all of these scatterings and these reflections and essentially just bend the light right around my particle so that the wave coming out on the other side looks undistorted. And I've essentially rendered this particle invisible. So we can see a little, if we look a little bit more schematically, I can see over here that I need the light to bend the wrong way, because if I send it in, at first I need the light to bend in one direction to avoid my particle, and then bend in the wrong direction to come back out the other side as if nothing's happened. So these metamaterials giving us this control allows us to start to hide small particles. There's still a lot of challenges, so you don't have to worry that there's someone sitting in the empty seat next to you in an invisibility cloak, because we don't quite have these perfected yet. We can mainly do this if we use really long wavelengths. So I mentioned before that with our metamaterials, each unit is much, much smaller than the wavelength. So if I make something at a microwave wavelength where my wavelength is very, very long, I can essentially make metamaterials just that I can place on a table. They're very large units. Or we can do this with really small particles, so micron-sized particles, for example. Another really interesting thing that I can do, so Andy mentioned conventional lenses. They can focus light down. And these are really sort of a fundamental object in light science and optics, and have been around for over 1,000 years now. But what we can do now, because of the fact that I have these units that I can design to send my light wherever I want, I can now, say, take a normal lens, which would be about 1 centimeter thick, and I can do the same thing in 20 nanometers. This means we can make essentially flat lenses, where my lens is now 5 million times thinner than this conventional optical component. So all of this has led to some really cool new areas that we're starting to apply these metamaterials. One of them is astronomy. You typically, in a telescope, have really complicated, really big, bulky optics, especially if you're going to send it into space. All of that weight starts to add up, and it's very expensive. So if we start to use these flat optics where we have a lens that's 5 million times thinner, and we can actually add new functionality just by designing these small units, we can make much, much thinner lenses in our telescopes. Holograms, another cool area that these metamaterials are being applied. So in a hologram, you essentially have this 3D projection where you can now walk around an object and it has perspective. Because with metamaterials we can send exactly the amount of light we want in whatever direction we want, we can start to build up 3D objects that are made of both red, green, and blue, so full color holograms. And then in these virtual reality headsets, for example, where we're taking the optics that are in this big bulky headset and making it much, much smaller, so you feel much more immersed. And then another area that's been quite interesting and gained a lot of interest for these metamaterials is, for example, biological applications where you have imaging, sensing, and then these nano antennas actually turn out to be really good objects to focus light energy down into really small volumes. So now one of the things that is actually in human trials is using these nanoparticles or nano antennas to actually attach to a cancer cell. I can shine light on the area where I know the cancer cell is, and then these little particles will locally fry the cancer cell. But I'll be glad to talk about this in some more detail afterwards. So we've been seeing how the nanoscale material in nature is shaping the world that we see. And Christine showed how the understanding of how we can make these materials is now allowing us to make them in the lab. So hopefully, as we continue to make this metamaterial technology better, we'll be continuing to shape the world we see well into the future. And thank you all very much for your attention, and I'll take any more questions. Yes?
Bend and the optical lenses are fascinating. Do you know anything about the state of optical computation, optical gates?
So that's not an area that I'm very familiar with, but I know that in general doing the actual computation on optical, like a light beam that has your information, is extremely difficult, and there's a lot of challenges that still need to be overcome there.
That are 7 nanometers.
Sure. So we use the same techniques that Christine talked about in her section, where we'll do photolithography or use electron beam lithography to make even smaller structures, and then we'll deposit material or we'll etch away material. And then we can put whatever pattern we want. We can put circles, we can put the V-shaped antennas that you saw. And yeah, so it's mainly with the technologies that Christine talked about. Yeah?
The nano lens stuff sounded interesting.
Sure.
Where is that at for like making eyeglasses that are thinner?
For making eyeglasses that are thinner. So in our group, there's actually a couple of companies now that we've been in contact for making these flat lenses. So it's not just, it's still a little bit far off from being in your actual eyeglasses or say in a virtual reality headset, but there is a route to actually put these into real industry.
Are there any nanostructures yet that can sort of change their shape in real time? Or is it all like you etch it and it's there?
So there are some structures that you can manipulate with, say, an electric field that will change shape very, very slightly. And you can do this at relatively fast time scales, but not extremely fast, so maybe millisecond. There's also something that's called a spatial light modulator that does something similar to metamaterials, but on a larger scale. And that also can manipulate the wave on, say, like about a millisecond time scale. But making nanostructures that can respond extremely fast, that would sort of lend to optical computation. And it's something that a lot of people are really interested in.
We have a question from the live stream, but actually from the previous portion of your lecture.
Sure.
Have you constructed logic devices out of light circuits?
So me personally, no. There's a lot of people who have done something similar with photonic crystals, but again, that's not an area that I'm very familiar with, making the logic circuits. But there's a lot of people that are working really hard in that direction, yeah. Okay. Thank you very much.